Imagine that you and your friend share a Netflix account. You want to make sure that you watch a series together as friends and that no one watches the series alone. You have a single password that you want to share between you and your friend in a way that none of you has the complete password and you can only figure out the password together. How can we do this? Let's imagine we have an 8-digit password that you want to distribute between you and your friend. You could just split the password in half so that none of you have the complete password and only you both can figure out the complete password. This naive approach seems like a reasonable solution, but there are two problems here. The first problem is that you and your friend have half of the password. So if either of you wants to brute force the rest of the password, all you need to do is try all possible combinations for the remaining 4 digits, which turns out to be 10,000 possible combinations. While this sounds like a lot of combinations, it is much less than the combinations you would need to try if you didn't know any of the 8 digits, which is 100 million. We can see that any person with a share of the secret can figure out the complete secret with much less effort. So, our aim here is to figure out a way such that even after having a share of the secret, you should still need to go through all 100 million combinations instead of just 10,000 combinations. In other words, the individual shares of the secret should not reveal anything about the complete secret, hence achieving perfect secrecy. What we need here is to add some randomness to our secret. We'll start with our original 8-digit secret. Then we'll generate a random 8-digit number, which will serve as our randomness. Now, all we need to do is add these two numbers, but the way we will add these numbers will be different than a normal addition. To make it easier to understand, we'll use a clock with 10 divisions, from 0 to 9, to perform the addition. Say we want to add 8 and 4, we'll start at 8 and move 4 divisions in a clockwise manner. As we can see, we ended up on 2. So in this case, 8 plus 4 is a 2. Similarly, we have a 7 and a 3. We will start at 7 and move 3 divisions clockwise. This gives us a 0. We can add all the remaining digits like this and end up with a new 8-digit number, which is our secret with some added randomness. You can pause the video here and try this yourself so you can develop an intuition for adding numbers in this way. Now, we'll share the random number and the random secret with you and your friend. The next step is to recover our secret from these two shares. All we need to do is to subtract the random number from the random secret. As you might have guessed, we'll perform the subtraction using our clock. We will start at 2 and move 4 divisions anti-clockwise. This gives us an 8. Similarly, we have a 0 and a 3. We will start at 0 and move 3 divisions anti-clockwise. This gives us a 7. We can subtract all the remaining digits like this and end up with our original secret number. This way of adding and subtracting numbers is called modular arithmetic. You can do a lot more than just addition and subtraction, but we'll discuss more about it at a later point in this video. Now, let's think about two things here. What benefit do we get from adding randomness to our original secret? Does it solve the problem of information leaks such that we can achieve perfect secrecy? And what if we used regular addition and subtraction instead of using modular arithmetic? Is there any benefit of using modular arithmetic at all? We'll first talk about the benefit of adding randomness to our secret. Suppose that you have the random secret. Let's try to see how can we find the secret number using just the random secret. Think about what two numbers can actually give us a 2. Here are all the possible combinations that can give us a 2. This shows that to find this individual digit of the secret number, we need to try 10 combinations. If you do this with all the 8 digits, we will end up with 100 million combinations. As we saw earlier, this is the same number of combinations that you will have to try if you have no secret share at all. So, this shows that adding randomness to our secret number mitigates the information leakage issue. Thus, a person with a share of the secret is as clueless as a person with no secret share at all, hence achieving perfect secrecy. Now, we will talk about why we need to use modular arithmetic here. Let's use regular arithmetic to add randomness to our secret. We'll take our 8-digit secret and a random number and add them to generate a random secret. Suppose that we have the random secret and we need to find out the secret number. What we have here is a very simple equation. We can plot this equation on a graph where the secret number is on the x-axis of a graph and the random number is on the y-axis. Each point on this graph represents a combination of the secret and the random number. There are some points on this graph whose sum of the x and y coordinate values is equal to the random secret that we know. If we plot all such points on this graph and join them, we will see that it is a line. Each point on this line represents a possible combination of values that you need to try to find the secret. If you count the number of points on this line, it's equal to the random secret number itself. So, the smaller the random secret is, the fewer combinations you will have to try. We can easily see that it will be easier to brute force the secret number if we use regular arithmetic compared to modular arithmetic. Let's try to visualize how using modular arithmetic makes it harder to brute force the secret. When we add the secret and the random number using modular arithmetic, we basically have 8 independent equations instead of just a single one. In order to plot this, we will have to use 8 clocks. Each clock can have 10 different combinations that can give us the respective sum of each equation. So, no matter how big or small the random secret number is, you will always have to check all possible 100 million combinations. Feel free to take a moment and think about how, just by changing the way we add 2 different numbers, we have made it a lot harder to brute force the secret. While it is not clear at first, this small change in using modular arithmetic increases the security of our secret sharing system by a lot. To recap what we have learned until now, we started by sharing an 8-digit secret between you and your friend, and we mentioned that this naive approach has 2 problems. The first problem was to find a way to share a secret such that a person with a secret share has the same probability of brute forcing the secret as a person without a secret share. As we saw, adding randomness to our secret and using modular arithmetic helped us to solve this problem. Now let's discuss the second problem. With the current secret sharing system, we need the secret share from all the friends to recover the original secret. Say, if we had a group of 10 friends instead of just 2. As we add more people to our secret sharing system, there is a higher chance that someone could lose their secret share or just refuse to share their secret share, at which point the secret cannot be recovered. A better secret sharing system would allow us to recover the secret with just a fraction of the people in the group. So, if we have 10 friends in our group, a better secret sharing system would be where any 2 friends can come together to recover the original secret. In order to solve this, we'll use a 2D graph. Our secret will be represented by the value of the y-coordinate at x equal to 0. Let's suppose that our secret is 0, so that it is easy to work with the numbers. Next, as we did with our secret password, we need to add some randomness. So, in order to introduce some randomness here, we'll choose a random point in this graph. Now, once we connect these 2 points, we have a secret line. Let's try to understand what this line means here. Say you chose 10 different points on this line. Each of these points represents a secret share. You can distribute these 10 coordinate values with a group of 10 friends. Now, any 2 friends can come together and draw a line between their points and extend the line to x equal to 0. This will reveal the secret point, and hence the secret value, which is 0. Note that if you take any individual secret share or a point, you can make infinitely many lines through it, which will intersect the y-axis at infinitely many points. So to summarize, any individual secret share or a point does not reveal anything about the original secret, hence maintaining perfect secrecy. If you have 2 or more points, you can draw a unique line that will recover the secret point. This scheme works for cases where you want any 2 people out of a group to recover a secret. What if we want to create a scheme where we want any 3 people out of a group to recover a secret? To do this, we will start with our secret point, 0, 1, and choose two random points, 1, 0 and 2, 1. Similar to how we use a line to connect 2 points, we can use a unique curve that goes through all 3 points. Such a curve is called a quadratic curve. You can choose any number of points on this quadratic curve, say for example 10 points, and then distribute these 10 points among the 10 friends. Then any 3 friends can come along and recover the same quadratic curve that was used to create these 10 points. Note that if we pick any 2 points out of the 10 points, you would find that there can be an infinite number of quadratic curves that can pass through the 2 points, each of which will intersect the y-axis at different points. This means that no information is leaked about the secret if you have less than 3 points. By now, you might be able to see a pattern here. In the first case, where we wanted 2 shares to be able to recover the secret, we used a line, which is a polynomial of degree 1. The degree of a polynomial is represented by the highest power of x in the equation of the curve. For example, in the case of a line, the highest power of x is 1. Hence, it's a polynomial of degree 1. In the second case, where we wanted 3 shares to be able to recover the secret, we used a quadratic curve, which is a polynomial of degree 2. Similarly, if we want 4 shares to be able to recover the secret, we will use a cubic curve, which is a polynomial of degree 3. This pattern follows as we increase the number of shares needed to recover the secret. Now, one question that you might have in your mind is how can we recover the unique curve given a set of arbitrary points? We can do this using something called Lagrange interpolation. Let's start with a simple example of 3 points, 1, 4, 2, 9, and 3, 16. We'll denote the curve that goes through all the 3 points as S of x. Note that we only care about the values of the curve at these 3 points. So, following this logic, we can say that S of x can be represented as a combination of 3 quadratic curves. First, we have f of x, which has a value of 4 at x equal to 1 and 0 at x equal to 2 and 3. Next, we have g of x, which has a value of 9 at x equal to 2 and 0 at x equal to 1 and 3. And lastly, h of x, which has a value of 16 at x equal to 3 and 0 at x equal to 1 and 2. If we add the values of these 3 quadratic curves at x equal to 1, 2, and 3, we will get the values that satisfy s of x. We can rewrite these 3 functions such that we can generalize Lagrange interpolation for any number of points later. Let's convert these quadratic curves into equations. We can write f of x such that it is 0 at x equal to 2 and 3. For this equation, the value at x equal to 1 is 8. But as we want the value to be 4 at x equal to 1, we need to divide f of x with 2. Similarly, we can write g of x such that it is 0 at x equal to 1 and 3. For this equation, the value at x equal to 2 is minus 9. But as we want the value to be 9 at x equal to 2, we need to divide g of x with minus 1. Lastly, we can write h of x such that it is 0 at x equal to 2 and 3. For this equation, the value at x equal to 3 is 32. But as we want the value to be 16 at x equal to 3, we need to divide h of x with 2. We can now add the 3 curves one by one to get s of x. You can follow this same process for any number of points to recover the desired polynomial. In theory, this seems like a perfect way to share secrets. Let's try to go through a practical example and see if this works as we expect it to work. Suppose that our secret is 0, 0, and we can choose a random point, 3, 1. This gives us the line s of x. We'll choose to share 2 secret shares, s of 3 and s of 1. Here, s of 3 is equal to 1, and s of 1 is equal to a recurring fraction. While this is close to the actual value, this is not the exact value. So if we try to recover the line using these values, we'll get a line that is slightly different than the original secret line. we will try to print out a result for S of 1 with higher precision to see if we can get closer to our original secret line. Somehow, we start to see random numbers instead of a recurring sequence of 3s. Why is that? This is a consequence of how computers represent numbers under the hood, which are called floating point numbers. Let's suppose that in order to solve this issue, we can try to update our polynomial, s of x, such that it does not involve any fractional values. We'll choose to share two secret shares, s of 3 and s of 1. Here, s of 3 is equal to 7 and s of 1 is equal to 3. Assume that we have the secret share s of 3, and we are trying to guess the secret value at x equal to 0. If we assume that the value of the secret is 2, the two secret shares for us would be 0, 2, and 3, 7. The line that goes through these 2 points is the following. The problem with this line is that at x equal to 1, the value turns out to be a recurring fraction. Now remember that we decided that we will be only working with polynomials that do not have a fractional value. But as we can see, if we assume that 0, 2 is a secret share, it violates our rule of no fractional values. This means that 0, 2 cannot be a valid secret. So even with just the knowledge of a single secret share, we are able to rule out the possibility of 0, 2 being a possible secret. This means that we no longer have perfect secrecy, as we are able to deduce some information about the secret without having a threshold number of shares. What we can observe here is that even if we try to avoid the fractional values in our secret polynomial, it can still affect the security guarantees of our secret sharing scheme. What would solve this issue for us is if we could figure out a new form of arithmetic where we can make sure that all operations such as addition, subtraction, multiplication, and division always lead to an integer. Let's try to do this using modular arithmetic. To recap what we learned about modular arithmetic earlier, we start by defining a modulo, say 5, and then we can create a clock with 5 divisions, from 0 to 4. Next, we'll define all operations like addition, subtraction, multiplication, and division. A very nice thing about using modular arithmetic here is that all operations will always result in a number from 0 to 4. Hence, we will not have any precision issues that we encountered while using regular arithmetic. Let's try to add 4 and 2. We'll start at 4 and move 2 divisions in a clockwise fashion, which gives us a 1. We can subtract 2 from 4 by starting at 4 and moving 2 divisions anti-clockwise, which gives us a 2. Next, we'll multiply 2 by 3 by starting at 0 and moving 2 divisions clockwise 3 times. This gives us a 1. Finally, let's try to divide 1 by 3. We can write this as multiplying 1 with the multiplicative inverse of 3. Now, the way we define a multiplicative inverse of 3 is by trying to find a number which, when multiplied by 3, gives us a 1. As we just saw, 2 multiplied by 3 is 1, hence the multiplicative inverse of 3 is 2. We can now replace the value of the multiplicative inverse as 2. This reduces our problem to 1 multiplied by 2, which gives us our final answer. This basically covers all the things we need to know to use modular arithmetic with our secret sharing scheme. Given that we can now even handle fractional values as integers, using modular arithmetic makes it practically feasible for us to implement our secret sharing scheme while maintaining perfect secrecy. There are a few last questions that we can still ask here. Does this new form of arithmetic work for any modulo value? And what are finite fields and how modular arithmetic is related to them? Let's try to answer the first question by choosing a new modulo, 6. As you would expect, addition, subtraction, and multiplication would work without any issues. Now, as an exercise, try to find the multiplicative inverse for 2. Feel free to take a moment and think about it. As you might have realized, there is no multiplicative inverse for 2 when we use modulo 6. In fact, 2, 3, and 4 don't have multiplicative inverse in this case. Hence, we cannot calculate fractions like 1 divided by 2, 1 divided by 3, or 1 divided by 4. So, it seems like our new form of arithmetic does not work for all modulo values. There is a specific class of modulo numbers for which our new form of arithmetic always works. This specific class is prime numbers. For example, here is a table for modulo 5, and here is a table for modulo 7. As you can see, in both cases, we have multiplicative inverse for all the numbers. This answers our first question. Next, let's briefly talk about finite fields. The new form of arithmetic that we just invented using modular arithmetic is one of the examples of a finite field. Any set of numbers, or elements, can form a finite field if it follows the following rules. First, there is a specified number of elements. In our case, the modulus value we chose decides how many elements we will have. For example, in the case of modulus 5, we have 5 elements, and in the case of modulus 7, we have 7 elements. Secondly, addition, subtraction, multiplication, and division operations except 0 are closed, meaning that performing these operations on any 2 elements of the field will result in another element within the field. As we saw earlier, if we chose a modulus value that is not a prime, for example 6, we found that in some cases division was not defined for some particular elements, whereas if we chose a prime modulus, let's say 5, then the division is defined for all elements. Lastly, there is a set of unique additive and multiplicative identities that should be satisfied by a set of elements to form a finite field. Let's do a final recap of all the things we have learned. We started with a naive way to share a secret between you and your friend, where we solved 2 main problems. We added randomness to our secret using modular arithmetic to achieve perfect secrecy, where we don't leak any information about the secret, hence achieving perfect secrecy. We used graphs to represent our secret and randomness as points to create a secret sharing scheme that could handle scenarios where we can recover our secret with a fraction of the total distributed shares while maintaining perfect secrecy. Next, we looked into Lagrange interpolation, which showed us a method to recover a secret curve given we have a threshold number of shares available. Once our secret sharing scheme worked in theory, we tried to create a practical implementation for our scheme where we encountered some limitations regarding the precision of fractional values due to the way computers store and operate on numbers. Next, we attempted to update our polynomial to eliminate the use of fractional values. However, in doing so, we sacrificed perfect secrecy due to the presence of fractional values. Finally, we devised a secret sharing scheme using modular arithmetic, where we can make sure that all operations such as addition, subtraction, multiplication, and division always lead to an integer, hence solving the precision and perfect secrecy issues altogether. In addition to sharing secrets, concepts like Lagrange interpolation have a wide range of applications. One such application is in data encoding and recovery. For instance, these concepts are used in encoding and reading data from CDs and QR codes. By using techniques like Reed-Solomon codes, which is an application of Lagrange interpolation, even if a CD gets scratched or QR codes are partially damaged or obscured, it is still possible to recover the original data accurately. This ensures data integrity and reliability in various real-world scenarios. The ability to reconstruct data from partial or corrupted information is a powerful capability provided by these mathematical principles. There are many other rabbit holes you can explore with the things we learned in this video, some of which we will cover in future videos.